Hi there, this is Angelina and welcome to my channel. I am currently making a series on learning SQL with Microsoft SQL Server from beginning to advanced. I am kicking it off with the explanation of some database properties and concepts before we get started with the actual querying of data with SQL. This video focuses on explanation of relational data modeling and databases, what they mean and why they are important. So without further ado, let's get started. Relational data modeling. Data modeling is the first stage of a software development lifecycle, or the first stage of implementing a data strategy or a database solution. It is where you design and create a visual description of the business process and structure of the database by incorporating the business and the technical requirements. Data modeling is like a blueprint of the database structure. It is important for data modeling to happen because it helps you to stay organized and on track. Business can have direct hand in defining the core business rules, which means there will be fewer revisions during the implementation phase. That means we can cut costs and we can achieve results faster. It also helps to understand the business process. The process of data modeling forces you to define the business and its process in ways that others can understand. It is actually difficult to come up with a data model if you do not clearly know how the business is operating. Data modeling comes in three phases. We have the conceptual phase. This is the big picture module, okay? It represents the overall structure and content, but not the detailed plan. This is the part where you know the type of entities that are going to be in your data module. At this point, if you're an e-commerce business, you know that you serve customers with products. So you probably have a product entity, sales entity. You have a fair idea of all the tables or the entities are going to look like. It's like the higher level blueprint. Then we have the logical phase. This adds more details to the conceptual phase. It describes the database content. Here we consider the user requirements and see what restrictions we have. Over here, if we have a customer entity, we start to understand that we want to know the customer name, where they live. So we want to have the customer first and last name. We want to have the customer location, like the address. This is where you start to add all those details. And you start to create the relationship that would exist between the multiple tables that you may have. Over here, you also start to use softwares like Microsoft Visio or Erwin to design your module at this point. The last phase is the physical phase. This is the phase that describes the specifics of how the logical module will be achieved. Okay, it has enough details for the design to be actually implemented. This is the phase where you add your technical requirements such that you know what the data types are going to be like. You know the size limits, the row limits, the different domains, all those details. This is where you have them. And this is where you actually create a test design, a physical design on some type of hardware to see how the whole strategy is going to look like. Next, we discuss entity relations. Now I have this diagram where I have three entities shown. I have the course entity, the instructor entity, and the student entity. An entity represents a real thing, okay? Because instructors are real, courses are real, and students are real. A relation represents a connection between the different entities, okay? So the ER diagram actually shows you multiple entities and how they relate to each other. It's just a graphical representation. Now, what you see here is a crow's feet. I don't know how to say it. A crow's feet notation design, where is showing you more analytical view or technical view of the entity relation. By looking at this image, you should be able to determine the type of relationship that exists between the entities. But before we talk about the relationships, let's talk about keys. On there, we see PK representing primary key. On the course entity, the course ID is the unique identifier in the course table. Meaning, if you want to find a course, by going with that ID, you'd find each individual or unique records in that table. Same with the student. The student ID is the unique identifier in the student table. However, in the instructor table, We have the instructor ID and the course ID, and now we see FK, which is a foreign key. A foreign key simply means a representation of an ID from another table. Okay, so right now the course ID is a foreign key to instructor table. Meaning if you want to connect a course and an instructor, you can join on those IDs. Now, because we have instructor ID and course ID together at the top, it shows that there's a composite key. Meaning to have a unique record in the instructor table, you need to combine the instructor ID and the course ID to be able to come up with a unique identifier or a unique record in the instructor table. We also have relations or relationship. Over here, I show a one-to-many relationship between the course and instructor table. But then the one-to-many relationship, it can either be mandatory or optional. Now, the relationship I have created between the course and the instructor, I'm saying that an instructor cannot exist without a course. So the relationship between the course and instructor is mandatory. Whenever there's a mandatory relationship, there is this bar, like I'll circle it sometime, but the lines. And whenever the relationship is optional, you see a circle. Now the notation, you see, it looks like a feet. The lines I'm showing over there, it looks like a feet. That's what we call the crow's feet notation. Okay. And now a one-to-one relationship means that in the course table, there's only one record from the course table mapping to just one record in the students table, for example. A one-to-many relationship would mean that there's one record from the course table mapping to more than one records in the students table. And a many-to-many relationship means that there could be many courses in the course table mapping to many students in the students table. However, the diagram that I show here, I only show a one-to-many relationship, a one-to-many relationship. Okay, so that is an entity relations diagram. Now that we know what data modeling is and why it is important, let's quickly look at what relational databases are. First of all, data simply means information. And a database organizes a collection of structured data to make it easily accessible and manageable. Now, the term relational database was invented by E.F. Cord at IBM in 1970 during his research paper. Now, the research paper was called A Relational Module of Data for a Large Shared Data Banks. So then, what is the relational module of data? The relational module organizes data into one or more tables of columns and rows with a unique identifier, identifying each row, according to Wikipedia. Okay, so a table also means a relation, and a column also means an attribute, and then a row can also mean a record or a tuple. So in an entity, there could be attributes and records, meaning there could be rows and columns. That is what a relational database is. Now, to have a relational database, you also need some type of software that can help you to store and manage or query the data from your relational database. Those are what we call the relational database management systems. They help you to do like CRUD operations, meaning your create, your read, your update, and delete operations. Now, examples of relational database management systems include Microsoft SQL Server, Oracle, MySQL, Postgres, and Postgres is an open source relational database management system. Most of these items that I have here, some of them are free to use, some of them are not free to use. For the video series that I'm making, I'm going to be focused on Microsoft SQL Server. Now, why are relational database management systems very important, or why do we use them? The first thing is scalability. They can handle both small and large volumes of data. And standardization of data. Once your data is transformed into columns and rows, your data is standardized and you can query it with SQL, which is a structured query language used to access data from a relational database management system. It also helps you to achieve data integrity. Data integrity is almost like the backbone of every relational database. It helps to keep your data very meaningful. It also gives you ease of maintenance and simplicity. Once data is systematically stored, and modeled in your tabular format, columns and rows. It can be easily accessed, debugged, tested. Whenever you need to have some type of maintenance on it, it is easy to do that. There's also flexibility. Relational databases gives you the flexibility to add tables, alter tables, add and remove data, remove columns and rows at any point in time. And the last one that I have here that it helps you, the last one that I have here is that it helps you to retain data consistency. It helps you to retain data consistency. This is because relational database management systems are asset compliant, and it is easy to add or modify items whilst maintaining this consistency. When I say asset, I mean a database property, which I'll cover in my next slide. So now we come to asset properties or asset transactions. Okay, these are properties of a database that helps you to guarantee some type of validity, even in events of error or failure. The A, okay, so asset is an acronym. Asset is an acronym. A in the asset means atomicity. Okay, this means that transactions will be all or nothing. There will be no intermediate transactions. It will be all or nothing. So the whole transaction, which is a set of read and write operation, is either going to be processed or nothing is going to be processed. For example, we need to transfer, let's say, $300 from an account. Okay, so there is a Ken's account of a balance of 1,000 and an Angie's account of a balance of 1,200. The operation is to deduct $300 from Ken's account and add it to Angie's account. So all operation in this set must be complete. In an event of a system failure, okay, if the system fails to add the amount to Angie's account after deducting from Ken's account, the whole operation has to be reverted. Because there shouldn't be an instance where the money was deducted from Ken's account, never made it to Angie's account, but Ken can't see his money. This is why we say the transaction must be all or nothing. And this is a perfect example of atomicity. The next thing is consistency. Consistency here means that data will always be valid for each transaction. Only transactions that abide by certain constraints and rules are written into the database. Otherwise, database will keep the previous state. That is consistency. The next thing is isolation. Isolation means that transactions will not interfere with each other. Transactions are processed independently and securely, and the order of the process does not even matter. If you're performing multiple transactions on a single database, operations from any transaction should not interfere at all. For example, if there is any other transaction going on between, let's say, Angie and Andrew, it should not make or affect any transaction between Angie and Ken at the moment. Both transactions should exist in isolation. The last is durability. Durability means that transactions will always remain committed and final. Completed transactions are saved to the database even in cases of system failure. So it may happen that as you try to save something into your database, the system has crashed. Okay? The fact that the system crashed does not mean that you're about to lose, let's say, the operation or the transaction you started. It would remain committed even in an event of failure. So this is what asset properties of a database means. Okay? Now we move on to different types of databases. We have the OLAP and the OLTP. The OLTP means online transactional processing. These databases capture real-time transactional data. They are used for less complex queries. The types of queries for these databases are for read, insert, update, and delete. Now we also have the OLAP, online analytical processing. These databases are for complex analytical and ad hoc queries, including aggregations. These are what we typically call the data warehouses, okay? The OLAPs are what we typically call the data warehouses. So the differences between these two databases are that one is used to capture real-time information and it's not for complex queries, but the other is more for analytical purposes and is supposed to be very read efficient. So now we move on to the structure of a database. Okay. The first one that we will discuss is normalization. The focus of normalization is to reduce redundancy. Redundancy here means that keeping multiple copies or duplication of data in multiple places in your database. Normalization is used to prevent anomalies. Anomalies for delete, insert, and update. This helps us to isolate data so that changes do not propagate throughout the database, affecting other things that we did not intend to affect. Now, there are different forms of normalization. We have the first normal form, the second normal form, and the third normal form. We also have the fourth, the fifth, and the sixth normal forms. But for the purpose of this discussion, I'll limit it to only the first to third. These are the normal forms that I've seen in a production environment. So now, how do we reach a first normal form? For a table to reach the first normal form, it has to have atomic values. That means each cell must contain a unique and a single value. The tables must also have relationship between other tables. So we have to separate the data such that we can create relationships between the other entities. Once we have the atomic values, where we have unique records into each single cell, we have achieved the first normal form. And once we keep the relationship between tables with some type of referential integrity with a foreign key, we have also achieved the first normal form. So these two must go together. Now, to achieve the second normal form, you have to have reached the first normal form before you can even come to the second normal form. So after reaching the first normal form, you also have to make sure that all the columns in the table must rely on the primary key, meaning you have to make sure that all non-prime attributes are fully dependent on the prime attribute, where the prime attributes are those that stand as keys or as candidate keys. Okay? So after you achieve your first normal form, then you make sure that all the records are relying on the primary key. Then you have achieved your second normal form. For the third normal form, you must have achieved the second normal form first. And over here, you also have to make sure that there are no transitive dependencies, meaning all non-prime attributes are not transitively dependent on the prime attribute. What do we mean by transitive dependencies? In the third normal form, we expect you to move from 1 to 2, then 2 to 3. We don't expect you to move from 1 to 3. Once that happens, of moving from 1 to 3, it means you are doing a transitive dependency. So that is what a third normal form means. Okay? So the only issue with normalization is that once you have the tables in your tables separated or your data separated into different tables, to pull even the most simplest report, you have to have multiple joins because you have to pull data from multiple places. And joins could be expensive depending on your data set. Okay, so this is one of the setbacks of normalization. The second structure is denormalization. It is a strategy used on a previously normalized database to increase performance. So after you have normalized your database, now you want to be able to do reporting on your database. You want to now denormalize some of your data such that you can introduce redundancy, meaning you start to introduce duplications in the data set so that you can retrieve data faster. That is what denormalization means. Okay, so an OLAP, which is a data warehouse, is mostly denormalized, where a transactional or regular database is normally normalized. Okay, so simply put, normalization is a database where there are no duplication of data, where denormalization is a database with duplicates of data, in simple terms. So these are the two main database structures that we have. So we want to go through some examples of normalization. Now we just have a general table here. We have it, the author name, the year published, and books published by the author. Okay, and we have the publication type, which is the fiction and the nonfiction. Now this table is not in any normal form at all because there are multiple items in one cell. We have the nonfiction A, nonfiction B, and the books published. Now to attain the first normal form, we have to break down the books published into each individual cell. So now we have 5 entries instead of 2 entries because we broke down the books published. So now instead of book published, we have book titles. This is the first normal form. However, we still see that we have a lot of duplicates of data in here. We have the author name, the year published, and the type of publication all duplicated. So we want to try to break it down further. To achieve a second normal form, we have broken down the book titles, and now we have unique records in the book title table. And for the author name and the type of publication, now we see that it's actually only 2 records. We don't have Kenneth repeated 5 times. We only have it twice. Okay, so this is second normal form. Now, for the third normal form, we have broken down the type of publication and removed the author into a different table called the author table. So now we only have one author in the entire table. We only have one author, which is Kenneth. And now that author is being referenced into the publication type table, which is the fiction and nonfiction. Okay, so right now we move from a not formalized table to the first normal form, the second normal form, and the third normal form. So in summary, we looked at what is data modeling and the different phases of data modeling. We also looked at what relational databases are and why they are important. We also discussed the ACID properties of the database. And finally, we discussed the structure of the database, normalization and denormalization, as well as the normal forms. I hope you found this video very informative. The next video will focus on the installation of SQL Server and all the relevant software to help us to get started with the learning of SQL. Do give me your feedback in the comment section and do support by subscribing to my channel. Thank you for watching.